Okay, thanks. Shall I start? Okay.
Yes, go ahead.
Good morning. Welcome to the Intelligent Maintenance Conference. I'm Yuan, a second-year PhD student in the chair of Intelligent Maintenance Systems, and I'm focusing on the reinforcement learning and its applications, especially in the maintenance domain. And today's topic is prescriptive maintenance with deep reinforcement learning. In the past 10 years, database approaches have made a lot of success, such as image classification, detection, and segmentation, machine translation, as well as eye disease diagnosis. Also, there are many methods has already been successfully implemented on the maintenance domain. So, for example, the fault detection or anomaly detection. And use domain adaptation approaches for more applicable fault diagnosis in the industry, as well as prognosis like the remain useful life prediction. Well, I believe in previous presentations, and you will be very familiar with the predictive maintenance, that it predicts the remaining useful life, anticipates the failure, reduce the impact of the failure, determine the optimal points in time for maintenance intervention. But since we already can reach it, is there any possibility that we could do something to prolong the remaining useful life, like go one step further? And this is prescriptive maintenance. The main goal of the prescriptive maintenance is to develop the algorithm that's not only able to predict the required maintenance measures, but also to prescribe an optimal course of actions based on the current system state. Let me give you an simple example. Imagine we are driving a hybrid vehicle, and based on the historical data, the prognosis says that the remaining mile is around 80 kilometers. However, the current navigation to home is around 100 kilometers. So maybe we need to adjust our driving mode from the sport to eco, or find the shortcut. Sorry. And to solve this kind of sequential decision-making problem, reinforcement learning is a promising direction or methods. Reinforcement learning is a subfield of machine learning which focuses on how an agent could interact with the environment to achieve highest cumulative reward. And the reinforcement learning is, like I said before, is to solve the sequential decision-making problem. And here is a control task, like very classical reinforcement learning task, balancing the cart pole by controlling the lateral force and trying to balance the cart pole in the middle. Different with other machine learning approaches, there is no supervisor or label data. The agent learning from trials and errors. And in this case, in reinforcement learning, the feedback may be delayed. What this mean? Generally, reinforcement learning aims to control something in a period of time to achieve some objects, which means the final result is the thing we are aiming for, which may delay. For example, in this case, we would like to balance the cart pole in the middle. Of course, we could use a large force and push it into to the middle and get a super high immediate reward or feedback. However, then the accelerate will be high due to the large force and make the pole unstable and falling down. So time really matters in reinforcement learning, and the data is not ID anymore because action will affect the subsequent data it's received. Maybe you're still a bit confused, and don't worry, I will explain with more examples. Well, in the past few years, reinforcement learning has already made a lot of success. For example, the DeepMind AI controls the Google data center cooling system and reduce the cooling bill by 40%. And OpenAI's agent defeated the world's top professional teams on a Dota 2 games, which is the most challenging task in the world. It's based on only the raw image to control, which can not be done by any other approaches, and we call it end-to-end control. Also, in the ETH robotics group, they use reinforcement learning to plan high degree of freedom joints trajectory and let select robots running more natural and faster than before. Of course, the AlphaZero, it's already the undefeated Go player in the world, starts without any human knowledge. And now reinforcement learning start to be used on AutoML, like design neural architectures, twin hyperparameters for deep learning tasks. I believe now you see that what kind of problem reinforcement learning can do. Let's go back to the decision making in the maintenance domain. So in maintenance domain, it actually could be summarized with different. So the maintenance actions or maintenance related actions could be summarized with different time scale and with different system integration level. The decision making time scale can range from real-time response in milliseconds to strategic process design. The system integration scale can range from component level to networks of distributed system. For example, still driving a car, we notice that the remain mile is not sufficient, so we need to adjust our driving manner, and this is operational level. And but when the energy storage degraded, the prognosis for the remaining miles may not accurate and will influence the following operational decision making. Then we may need to do the real-time calibration and to make the prognosis more accurate. And so this is the component level calibration. And to higher level route scheduling of a long trip, that will be the process optimization. So, okay, let's see the first case, equipment operation level, power allocation. Multi-power source configuration has become widespread in many different applications. One of their main challenges is design the optimal power distribution strategy between single power source. Here we target on the most typical system, multi-battery system. Since these batteries do not have same initial states, even under the same load profile, the discharge curve will be different. And in this figure, it's a discharge curve, and since the y-axis is the voltage, since this battery have different initialization, when the load equally distributes on these batteries, it will show different curve. And once a battery reaches the end of discharge state, itself and the entire system will be affected. So we need to develop a smart power allocation strategy that could allocate the power optimally and prolong the working cycle. And this is a challenge. So we develop a reinforcement learning based framework that can learn to allocate the income real-time low demand suboptimally. Well, one of the challenges is that I don't know how to use the printer. So, one of the challenges is that the real-time low demand normally is unpredictable since it comes from maneuver, and our agents could, based on only the real-time load, currents, and voltage information of all these batteries to make load allocation. With the help of reinforcement learning mechanism, it could learn to prescribe near optimal load allocation strategy to prolong the entire working cycle. With this framework, we shows quite good promising results. So on a 4-battery system, we successfully prolong the working cycle for 50.2% on average. And from the result, our strategy actually can maximize the working cycle that's run out of this battery at the same time without any waste of usability. You could see that when we applied the reinforcement learning controller, whatever the load it accepts, it could dynamically and smartly allocate to each batteries, and let's trying to let this battery run out or go to the end of discharge at the same time. Compare with the equal distribution, it prolongs a lot. Also, the framework shows good scalability. It could easily to scale up to 8 battery system and prolong the working cycle much more, like to the around 32%. Another case is the second battery case. So to reduce the life cycle cost and improve the sustainability of the batteries which are removed from the battery powered system with high requirements can still be integrated and reused in less demand applications. For example, the electrical vehicle, some batteries degraded and they cannot be used on vehicle, but some other stuffs. And in this case, the degradation dynamics as well as the discharge dynamics will be very different. Here is the plot for 4 batteries in different color on the left. Even under the same initialization and the same load profile, the discharge curve are distinctive, and some of these will be easily to get into end of discharge state. So in this case, when we applied the reinforcement learning load allocation management, the system, we prolong the working cycle for around 152 on average. Well, in this case, reinforcement learning shows good performance with 4 advantages. First, it's end-to-end with only the raw measurements and no further prediction, such as the state of charge, state of healthy, or remain useful life. It can learn a good strategy, which cannot be done by any other method because only the immediate or real-time current and voltage information cannot tell how much the power or electric left in the battery. And the scalability is good. And in this case, thanks to the reinforcement learning mechanism, it could target on global optimization without any prior knowledge. So next case, then we briefly discuss about another case. We talk about that if the remaining mile shows slow, we need to adjust our operation. But what if the kind of prognosis is not accurate? Normally we do prognosis, we will have a computational model to mimic the real assets. And sometimes there will be a reality gap between the computation model and the real assets. And bridging the reality gap is general and very important problem in science. And to fill the gap is sometimes called model calibration. Here, one of the challenges of the current approach cannot fulfill the real time. So here we develop a reinforcement learning framework for real-time model calibration, and it's by formulating the model calibration problem into a tracking problem. Here we target on the turbofan engine system, and the reality gap is mainly because of degradation. Because of the degradation of the real assets, the previous or unupdated computation model cannot match the reality. And we introduce a reinforcement learning agent. It controls. So the control things is the computation model degradation parameters. And by controlling it, it's trying to let the model output match the reality. Maybe it's still a bit confused. I will give you a more simple example. We mentioned before that we formulate the model calibration problem as by a tracking problem. Imagine we are driving a car and we follow a car in front, and we would like to know what is the operation made by the front driver. Of course, we cannot see him. So in this case, if we could solve the tracking problem, that we follow his path, and once we track very accurately, the inference is also done by solving the inverse problem. And based on this framework, it works well. We compare with multiple methods. The conventional method, like the unscented Kalman filter, is accurate, of course. And however, it needs to run the dynamic model multiple times. And in some cases, the dynamic model will be very slow to run the simulation. For example, the engine model, it cannot be real time. And of course, this problem could be dealt with regression. However, it need label data and do not normally cannot generalize well. And also we have reinforcement learning, and it shows both accuracy and fast. So before the previous advantage, compare with, in this case, compare with the supervised learning regression problem, it do not require the label data, which suits the industrial more, and it's also robust to sensor noise and model bias. Well, in the end, from data analysis perspective of view, the analysis approach could be abstracted into 3 different types, and the difficulty increase as well as the value. And the reinforcement learning is the method that's to tackle with the prescriptive analysis. And at the same time, in maintenance domain, the prescriptive maintenance is getting more and more hot topic in recent years. And we believe that reinforcement learning is a promising alternative in maintenance domain, especially for prescriptive operation. Thanks for your attention.
Thank you very much, Yuan.